Welcome to this video. In this video, I will be discussing regarding quantum data processing inequality. First, we will see a small example that classical and quantum cases differ greatly, in the sense that we can consider this joint entropy S of A and B, which is defined as or conditional entropy. We can consider the conditional entropy S of A given B defined as S of A and B minus S of B. Classically, S of A given B is a positive quantity. So S of A given B is greater than equal to 0. But in quantum mechanics, that doesn't happen. We can consider a state phi, which is a singlet state, 0 1 minus 1 0, and then we can take phi to be a joint state rho AB. So for this state, S of A and B will be simply 0, because you see S of A and B, if you can do the spectral decomposition or the eigenvalue decomposition of rho AB, it is simply the Shannon entropy, that is Pxy log Pxy summation with a minus sign. But here the spectral decomposition is already done and there is only one eigenvector associated to this. So that's why it is 0. So S of A and B is 0. And S of B, so we are calculating S of A given B. So S of B will be, you see, as this is a maximally mixed state, so S of B will always be like, this is this identity by 2. This is maximally entangled, so if you trace one of the part, that is trace out the A part, you will get identity by 2. And so the Shannon or the von Neumann entropy, or in this case Shannon, will be minus 2 times half log half. This is S of B, but this will be subtracted from S of A and B, so it will give us a plus sign. And so you see this quantity is minus 1. So S of A given B is minus 1 for this entangled state, that is a singlet state. So we get negative conditional entropies, and having negative conditional entropies are a signature of entanglement. But this doesn't happen in the classical case. So back to quantum data processing inequality. The idea is somewhat very intuitive and clear, and I will just give a few details, a bit of this intuition without proper proof. So suppose you process your, classically we have seen that if we process our data through channels or these noisy channels that have this this conditional probability distribution given, we get more and more uncertain. That is, we are more uncertain of X from the value Z than we are from Y, as I have shown here. So in quantum data processing inequality, what we have is that transitions are brought via CPTP maps. So suppose you have a bipartite state, rho AB, and suppose Alice on her part does nothing, but Bob makes some sort of a local transformation using some CPTP map, and he gets, suppose, this particular final state where Bob's map is mapping to some other person, that may be Charlie. So what this means is that Alice will be more uncertain about her state from Charlie than she will be from Bob. That is the same statement if you see intuitively in this classical case. And why this is true is because CPTP maps are associated with loss of information. You process something, pass through a CPTP map or channel, you will inevitably lose some sort of a correlation. Which is also seen by the fact that the trace distance always reduces on passing through the these CPTP maps. In other words, we can say this: the states become less and less indistinguishable. So this is one of the form of quantum data processing inequality. More formally, we have one more definition that is almost similar, where we require a bipartite state, but the state is obtained from a single state by its purification. So let's see that. So we define something called as an exchange entropy. That is an entropy associated with a state and a process. Still, we till now had entropies that relate states, but putting a process inside this entropy function is very difficult, and we need to define it properly. So the definition is as given below. Take a state, it is some sort of a bounded map over a Hilbert space. Use a purification B. In my very first videos I have talked about purification, and make this density matrix to a pure state such that if you trace out the B part, you will get back this density matrix. And now what you can do is that you can just evolve this density matrix using this particular operation. And what I have written here is that case where you take this pure state on AB space, where B is the ancilla and A is the original system, and then you evolve on the part of the system to get a new state. And then the entropy of a state and a process is simply defined as the entropy, the joint entropy of A and B, that we obtain from this purification evolution by this. So I must remind you that this is the von Neumann entropy, that is defined as minus trace of rho AB log rho AB. And also this state that we obtain from this evolution, this local evolution of this purification state, has some nice property that we call that it helps in defining something called as an entanglement fidelity. Entanglement fidelity between a state rho and an operation CPTP map is defined in this particular way, taking the inner product between the local evolution of the purification and the original purification. Psi was the original purification. So once you have defined this exchange entropy, or the entropy between a state and a quantum operation, we can a bit massage this equation, and what we get is that this equation can be written in the form of this particular matrix, where W is related to the cross operators of this CPTP map. So any CPTP map has a cross operator representation, has a Stein-Splint dilation. We have all discussed this. So in particular, the Wij, the matrix elements, are related to this particular form of cross operator. And once we have defined this exchange entropy, we can construct something called as a coherent information, which is almost same as this mutual information that we discussed, because originally we gave data processing inequality in terms of mutual information. So the coherent information between a state and a CPTP map is defined as the normal von Neumann entropy after evolution of this state by this CPTP map minus the exchange entropy of this CPTP map and the initial state that we have in hand. So given this definition of coherent information, we can actually bring the this data processing inequality in a very similar format to that we had of classical data processing inequality, because you see this kind of a single channel data processing inequality where you are applying locally is not what was present in classical state. So this is an equivalent formulation, but this is also another kind of a formulation. So suppose we take a state rho evolved by first CPTP map epsilon 1 and then epsilon 2, almost similar to the Markov chain. Then quantum data processing inequality states that this particular relation holds. You see, the relation is exactly same as this data processing inequality that we had, but the definition everywhere are different. Only the form, superficially they are same. So this is the von Neumann entropy of the initial state. It is always upper bounding the coherent information between the state and the first quantum operation, and then further this is upper bounding this particular coherent information. So in the classical case we had, if we have this x going to y going to z, where x, y, z are just random variables, we had h of x greater than equal to h of mutual information with y greater than equal to mutual information with z. So with this I will conclude this part by discussing something called as a degradable channels, and something called how to quantify how one CPTP map is more noisy than the another. So given you have one CPTP map epsilon 1 going from A to B and another going from A to C, if there exists a CPTP map that maps from B to C such that the second CPTP map can be written as a composition of these two, then we say that here this is actually not written correctly. What we say is that epsilon 2 is degradable to epsilon 1. You see, you can anyway, it's a definition, so I think you degrade epsilon 2 to epsilon 1, or maybe we degrade we degrade epsilon 1 to epsilon 2, because epsilon 1 is much more finer than epsilon 2 intuitively. So the point is it was written correctly, we degrade 1 to epsilon 2. So this degradability is intuitively we can say that, okay, initially we had one channel epsilon 1, having this channel epsilon 2 must be much more noisier than epsilon 1, because you are processing your data twice, by epsilon 1 as well as this CPTP map, and that is indeed correct. Degradability suggests noisiness. So for quantifying this noisiness, we say that suppose we choose this classical quantum states. So this is a classical quantum state where one of the part is a density matrix and it is tensor product with this classical distribution. So it is like sampling a density matrix using a probability distribution, and this is my U space and this part is my A space, and I locally apply this epsilon 1 map on my A space to map it to B space. You can check here, A going to B. Then I again take the same sampled distribution, the classical quantum state, and map it via this epsilon 2 map such that it goes to A goes to C. And these local mapping over these classical quantum states, I define them in this particular fashion, and then I say that epsilon 2 is much more noisier than epsilon 1 if intuitively I get more uncertain about my classical distribution after processing epsilon 2. That is what it means simply. So after processing by epsilon 2, I get the state gamma, and I am now more uncertain about my classical distribution U that is governed by this Qi. And the fact that if you can degrade your maps, that is, if epsilon 1 can be degraded to epsilon 2, then epsilon 2 is automatically more noisier. But now the interesting point is the point of reverse data processing inequalities. That is, if you see that your epsilon 2 is more noisier than epsilon 1, in the sense you are more uncertain about your classical distribution, can you directly conclude that, well, it must be the case that epsilon 1 must be degradable to epsilon 2? That means, is it possible to conclude the existence of a CPTP map by this kind of an inequality? And the answer is that it is not possible. So this part of inequality doesn't hold true. What must be done is that we must relax this condition a bit for it to hold true. So that's all for this video. In this video, I discussed some different kind of views towards this data processing inequality in quantum case. That's all.